Good evening. Today we'll talk about the next type of test called as chi-square test. Remember what is the chi-square distribution and how is it related to standard normal distribution. So we have standard normal distribution, which is normal 0, 1, and the square of standard normal is said to be chi-square. And if you look into the sum of k z square, then we say that is equal to 1 chi-square with k degrees of freedom. So this degrees of freedom indicates how many variables are considered in constructing that chi-square. So if we look into the data, if you have collected the sample variance, as we have looked into mean while beginning the hypothesis testing classes, I took some population items. I guess 2, 3, 4 was considered, and we selected various samples of size 2, and for that we computed mean, and I showed that if you look into the mean for all possible samples of size 2 and compute the mean for this statistic, which is called as sample mean, that follows again normal distribution with population mean mu and standard error sigma by root n. Now similarly, for every possible sample, if you could compute sample variance and see how the sample variance is distributed, you will observe that the sample variance is distributed with chi-square distribution. It follows chi-square distribution. So this assumption is valid if you are working under the normality concept. So if you have your population which is normal, only in the case you can talk about chi-square test, and particularly the test called as chi-square test for variance. Now this comes under the case which is called as a parametric test, where you are assuming that the population is normal. So we want to test the variance of a normal population. So in that case, you will be using what called as a chi-square test. So basically here h naught is you're testing sigma square to be equal to some number, let me use sigma naught square, or and then h1 sigma square not equal to less than or greater than sigma naught square. So this is the symbol what we use to indicate the population variance sigma square, and the test statistic here is given by, we indicate that by chi square is equal to n s square divided by sigma naught square, or you can also call this as sigma x minus x bar whole square by sigma naught square. When you have raw data, this always follows chi square with n minus 1, and here the sample variance is square is our sigma x minus x bar whole square by n, or sigma x square by n minus x bar square. So we are using the variance, and theoretically it is proved that the form of observed variance divided by sigma square that follows the chi-square distribution. And we know that chi-square is nothing but the standard normal square. The standard normal takes negative and positive value. When we square, it becomes just positive. So chi-square is always a positively skewed distribution. So here, if you observe the region, critical region, you will always have the curve of the distribution, which is a right skewed curve. So your chi-square value may start with 0. It may go on up to infinity. So even in this case, you can talk about one tail test, two tail test. So in the left tail test, you will reject the hypothesis for very low values of the observed or calculated value. So again, you will have some cutoff. Now I cannot just write that as minus k and plus k as we used in the previous test, because z and e were symmetric distributions. So whatever the alpha I fixed, the region was same. So if I observe a k here, I could easily observe minus k. But here there is no negative value for chi-square. Though my region is same, alpha by 2 and alpha by 2, the shape is different. So the points will be different because the distribution is not symmetric. So you will have K1 as well as K2. So for a two-tailed test, you will reject H0 if your chi-square cal is less than K1 or greater than K2. And for a one-tailed test, if you're talking about a left-tailed test, you reject the null hypothesis if your observed value is below K1, where the region up to K1 is alpha. For a right-tailed test, you will reject the null hypothesis if your observed value is greater than K2 in such that the region above K2 is equal to alpha. So the conclusion based on what type of alternative you have taken is similar, but reading the table value is different. So you can look into the chi-square value and one or two problems under this just to understand the method. But just remember the procedure to test the variance. No problems under this section will come. And it is not that widely used because it requires the assumption of the normal population. And if you are not very much sure that the population is not normal, then testing the variance becomes difficult. You have to look into the alternative, what called as non-parametric case. Now this test is under parametric. All the tests what we have discussed till now comes under the inference part of statistics called as parametric inference, and the tests are called as parametric tests. The reason is here we are breaking the hypothesis into simple statements consisting of what called as parameter of the distribution, or we are working under the case where the distribution or population is known, or some parameters are known, or properties are known. So those tests are called as parametric tests. So all our Z tests for mean, Z test for proportion, T test for mean, T test for population means, T test, and chi-square test for variance are all parametric tests. Now, the next type of inferential statistics is non-parametric test. Non-parametric comes into picture that you don't have the population parameters known to you, or the population properties, like what type of distribution is it from a binomial, is it from a normal. So very less or no information is known about the population or distribution. In that case you can apply what called as non-parametric test. And two of the most commonly used non-parametric tests under the chi-square test are chi-square test for goodness of fit, and then chi-square test for independence of attributes. And we use the third test most widely in the field of social science as well as medical science to see any dependency between two attributes which are further categorized into various sub-attributes. Chi-square test for independence of attributes. So we want to see the dependency, like whether the promotion is dependent on gender, or say high blood pressure is dependent on gender, the result is dependent on gender. So you are talking about two attributes and you are completely dealing with the frequency data or the count data. So we never know what the distribution of gender is, what is the distribution of results. So you just have the frequency under the linked attributes. So this is also called as test for multiple proportion. And since in a large sense the proportion follows normal distribution, and if I observe what is happening here, we are somewhat taking the square of that. So in that sense, in a large case, we can say that the converted proportions and its square becomes what called as a chi-square. So though we are applying the concept of chi-square, we use chi-square distribution. It is called as non-parametric because the distribution from where the data extracted, the properties, the parameters are unknown to us. This test, goodness of it, is used in the cases where you want to apply some theoretical distribution, like say binomial distribution or Poisson distribution or normal or any other standard distribution to a particular set of data. So you have observed a set of data, say number of decade 2, and then the frequencies or number of patients, number of persons. So you have a distribution. Now to study this particular distribution and to generalize the observed results on this sample to the entire category of the patients who have decay tools, we have to use the statistical concepts. Now, as said, number of decay tools are generally, it is Poisson distribution, number of accidents, number of births, etc. But whatever the data I have observed, does it actually follow Poisson distribution? That is a question. So how well or how good the fit is as a Poisson distribution, as a binomial distribution, that is, checked using this particular test. So you need to worry about that. And the procedure is also not asked because we haven't discussed the binomial and Poisson properties in detail. We have just looked, what is a Poisson distribution, what is a binomial distribution, how is it used in computing the probabilities. We have not talked about fitting a binomial distribution or fitting a Poisson distribution and so on. So we'll not worry about test for goodness of it of those cases. So that most commonly asked test widely used is this test, which is chi-square test for independence of attributes. Now, attribute, you're very much familiar by this time, I guess. Attribute are the qualitative characteristics which could be observed but cannot be expressed in terms of numbers. And you are selecting two attributes, and these two attributes are further, divided into various cases, maybe presence, absence, or, more than 3 cases also. And then for various combinations of these two attributes, which are divided into further categories, we look into the frequency from the observed data, and we try to establish whether those two attributes are indeed related or not. So if at all we say they are related, we say that the attributes are dependent. And if at all they are not related, we say the attributes are independent. So by default, we assume that the hypothesis that the attributes are not dependent, they are independent. So the test procedure is this. We'll write H0. Say the two attributes are independent. And if you're working with a special case, you can actually specify that. You can say the two attributes, gender and result, are independent. The two attributes, gender and blood pressure, are independent, and so on. Or you can always use a general statement which says the two attributes are independent. And the null hypothesis, the alternative hypothesis, is the two attributes are dependent. So you are finding evidence for the dependency and you want to prove the dependency. So you have come across a data which is telling that there exists a deep relationship or mathematical relationship between these two attributes. So you are gathering information to nullify this or to reject this and to prove this. So that's why we take this as the alternative hypothesis. And as said, it is easily assumed that in nature the two attributes are always dependent. Because of some other error or any other cause, the dependency is observed. The test statistic here is given by, procedure is a little bit lengthy here, you will have much of the calculations. So we say it is double summation OI minus EI, let me use J also, square divided by EIJ, I as well as J. And the square is only for the numerator, and this follows chi-square with m minus 1 into n minus 1 degrees of freedom. So what is this telling is, so you have observed some data, and let me just complete the procedure and later let me make you understand this. This is always a right tail test, one tail test. The reason is we are looking into actually the proportion, and we say we are having enough information to conclude that this is true, provided there exists, significant difference between OI and EIJ, OIJ and EIJ. So if there is, the values of OIJ, EIJ are respectively closer to each other, then that shows that they are independent, or there exists no gap, they are almost same. So in that reason, we say that the test is always a right tail test. So whenever you are applying this, so you will get K1 such that after your K1 up to infinity, the area is alpha. So you have level of significance alpha and degrees of freedom m minus 1 into n minus 1. What is this m? N? I'll let you know. And then we say reject H naught if your chi-square cal is greater than K1. And since I've used K2 for a right tail test, I'll just use K2 and we call this as chi-square calculated value. So in the chi-square, we have a tendency of, calling the table value for a right tail as K2 and table value for a left tail as K1. So that's why I've used K1, K2 here. So this is the procedure. So what you do, you will collect some data on two attributes classified into various cases, and M indicates the number of cases of first attribute, N indicates the number of cases. When I say I mean the categories, how attribute 1 is split, and the number of split of attribute 2, and M minus 1 into M minus 1 gives you the degrees of freedom. And your OIJ is the observed data. So whatever you are observing, the presence or absence of attributes in a selected sample or population, that is our OIJ. EIJ is the expected value. That is, if I say my attributes are independent, what should be the frequency or count in such case? So that theoretically expected value is called as expected frequency. So when we say observed frequency and expected frequency are almost close to each other, then that indicates independence. So we reject the hypothesis only if there exists a significant difference. So that's why we are talking about OIJ minus EIJ, and y square and divided by EIJ, somewhat, to convert the proportion so that we could come and say that it follows a chi-square distribution. So this is the setup or the test procedure of a chi-square test for independence. Now, to understand how it actually works, I have shared some question paper. Okay, fine. So in the first question paper, say July, August 2019, if you look into the second picture, question number 11 and sub question C. Test whether the attributes gender and result are independent from the following data. Okay, now the procedure and the formula what have given, that is different in the second PUC book, whatever you have downloaded, because in that second PUC, we only talk about a simple case where attribute 1 and attribute 2 is just split into two cases, two sub cases. And we have observed the count as ABCD. And when we substitute this ABCD in place of OIJ and EIJ and simplify, I get some other formula. But you need not follow this method. So don't follow the second PUC formula, but you can use the problems and apply the method what I teach. Because in your case, you could have a 3x3 or a 3x2 or a 2x3 case also. So let me write this problem. So this is 2019, July, August, question number 11C. So the question says, test whether the result and gender are independent. So we have 46, 28, 29, 12, pass, fail, and then male, female. So this is called as our observed data. So this is what we have observed in a particular college for a particular class when the results are out, and all these are indicated by OIJ. So we use I to indicate row generally, and we use J to indicate column. So if I say O11, that indicates first row, first column, and element belonging to that, or observed frequency in first row, first column. First row, first column is 46. First row, second column is O12, which is 28. Second row, first column, O21. Second row, second column, O22. Now, this is a simple case. You can have a case where I could, talk about a third gender. In that case, your gender has 3 cases, result has 2 cases. If you want to see or split the past class into first class, distinction, and then second class, then you can have 4 categories for result, 2 categories for gender. So in general, this table is said to have m cross n possibilities, or m into n possibilities, where m possibilities for first attribute and n possibilities for second attribute. In this example, both my m as well as n are 2. And to simply remember, you can say m is the number of rows, n is the number of columns in the observed frequency, in the observed table, observed frequency table. So these are all various frequencies. So you are counting how many males have passed in the exam, how many females have passed in the exam, how many males have failed in the exam, how many females have failed in the exam. That is, for every combination of attributes, you are obtaining the count. So have 2 case in result, 2 case in gender. So 2 into 2, you will get 4 cases, and these are those 4 combinational cases. Okay. So have you understood the general table? Okay, so can speak now. So in general, if you look into a general table, you will have m rows and n columns. But you need not worry, because we'll only give you at the most, 3 cases. I'll have O11, O12, etc. O1 and O21, O22, etc. O2 and O31, etc. So this is how the frequencies will be. So in general, I'll have m rows, OM1, OM2, etc. OM. So these are our observed frequencies, m rows and n columns. So we have understood what is our OIJ. So I need not worry about the the notation IJ, YIJ. Don't worry. I'll make the things very much simpler for you to understand. Just look into the computational steps. Don't worry about the notation. So I have OIJ. OIJ means observed frequency or observed count. And now we have to look into the EIJ values, which are the expected frequencies under the assumption that the null hypothesis is true. So EIJ indicates the theoretical frequencies, which we call as expected frequency, under the assumption that H0 is true. So when I say under H0, I mean H0 is true. That is, if in reality there is no relationship or no dependency between the attributes, so which is result in this case and gender in this case. In that case, we say our EIJ will be equal to the respective row total into column total divided by the grand total. So which you can simply write that as sigma Ri into sigma Cj divided by capital N, where capital indicates the total of all the values across row and column. Okay, so now you have to obtain your expected frequency for every case, and then you compute this double summation Oij minus Bij whole square divided by Eij. So I have to obtain this. Now how to obtain Eij? If you want a particular Eij, use its row total, multiply that by its column total, divide that by grand total. So the very first calculation here is obtaining the row totals as well as column totals. So we'll obtain row totals and column total. So in this case it is 60, 74, 20, 30, 41, and then 60, 75, 40, and the total of row total as well as column total, that is your grand total, which is 150. So sum all the values of the row totals, all the values of the column totals, that is your N. So you have your Oij table always given to you. You have to just compute Eij. To do Eij, you will first obtain the row totals and column totals. And now create the table with the same number of cells. If I have given 4 values, 4 cells, 2 rows, 2 columns, just create 2 rows, 2 columns, and then obtain the Eij. So there are 4 Oijs. So there will be 4 Eijs. If I take the first Oij, which is 46, for that I have to compute Eij. So Eij formula is row total into column total divided by grand total. Now for whichever cell or whichever frequency you are computing, use its row total and its column total. Now for 46, the row total is 74, column total is 75, and this grand total remains same for every value. So the first Eij is 74 into 75 divided by 150. We are not using Oij, we are just using the totals. Now the next value is this. For the number 28, its row total is 74, its column total is 40, grand total is 150. So 74 into 40 divided by 150. Next, for number 29, its row total is 41, column total is 75. So 41 into 75 by 150. For 12, row total is 41, column total is 40. So 41 into 40 divided by 150. Now compute these values. Those are your Eij. So take your calculators and simplify these values. 74 into 75 by 150, 48.2601. Of course, you might end up getting the values as decimal numbers. You have to consider the decimal because they are theoretical values. Theoretical values could be any real number. 41 into 75 by 115, 26.7391. 41 into 40 divided by 115, 14.26. Now, if you have correctly obtained your Eij, again, if you look into the row total and column total there, you should get the same numbers, which are 74, 41, 75, 40. So that is what we are, the underlying condition is, that's what. If there is no independency, whatever the scenario we are observing, we should split the frequency such a way that the total remains the same, but the internal values varies based on the assumption that we are giving equal weightage, equal chance of occurrence. The proportion is maintained same. So you can just have a quick look. 48 plus 25 comes to 73 plus the decimal part 7 and 2 6 goes to 74. And 48.2 plus 26.7 gives you 75. 25.7 plus 14.2 gives you 40. So please check that you are getting the same row totals and column totals to make sure whether your EIJs are correct. Now, after computing your EIJs, just obtain the chi-square value. Chi-square is given by double summation OIJ minus EIJ whole square by EIJ computed for all values across row and column. Now, whenever we have a tabular form of data in terms of rows and columns, then to obtain the total, we'll use double summation. That is the meaning. Because if you have just a column, like say X, and you're obtaining the total of that, we just use sigma X. But you have values, across row as well as column, then, technically, in order to obtain the total of all this, what you do is first you'll add these three, these three, these three, these three, then all those sum will be added again. So you're obtaining the total of the total. Total of the total. So we use this technique in order to, instruct the machine to compute the sum, and therefore we are using double summation to indicate the total of any particular table which has the rows and values in terms of rows and columns. Now, to make you understand, don't worry about this. Whatever the number of OIJs you have get the same number of EIJs. Now pick every OIJ with the respective EIJ, substitute that here and just put a plus mark and compute the value. So first OIJ is 46 according to the formula. Next I'll have minus, its EIJ is 48. Then I have to take the difference, take the square, divide by EIJ. So first value is 46 minus 48.2601 whole square divided by EIJ, which is 48.2601. So the summation indicates plus. Now just repeat this for all your OIJ and EIJ. Second OIJ is 28, so I'll have 28 minus its EIJ 25.7391 whole square by 25.7391. Then plus 29 minus 26.7391 whole square divided by 26.7391 plus 12 minus 14.2608 whole square divided by 14.2608. So I had 4 OIJs, so I'll have 4 terms in the expansion. If you have, another class, say, maybe pass class, fail class, and distinction class, then you'll have 3 and 2 values here, 3 into 2, 6. So in that case, you'll have 6 OIJs, 6 EIJs, and you'll have 6 terms in the chi-square or the test statistic. Now use your calculator and obtain the total. We call that as the observed value or the calculated value of the test statistic. So I said the procedure is a bit lengthy, but it is very easy. Very less number of formulas to be remembered. Only formula is the test statistic and how you compute EIJ. EIJ is its row total into its column total divided by grand total. Give me a minute so that I will compute this total. In the meantime, if you have a calculator, you can also do that. You can do part-wise, step this value plus this value. Or if you have scientific calculator, you can just compute everything in one step. So you see whatever is comfortable to you. 28 minus 25.7391 square divided by 7391. I'm getting this one 0.8540. So just by looking into EIJ, we can conclude. If you look into the numerical values of OIJ, EIJ, in almost all the cases, they are very much closer. 48 and 46, 25 and 28, 29 and 26, 12 and 40. So if that happens, what we are observing in the nature and what we are expecting, they are almost the same. So you know already what the conclusion is. And as said, our test is a right tail test. Right tail chi-square test always indicates that you will reject the hypothesis for a large value of the observed, because you are talking about chi-square which is from 0 to infinity. So for a larger value only, we will reject the hypothesis. Whenever you get an answer which is very much closer to 0, and in most of the cases in these tests, you will always accept the hypothesis, but cannot take a call. You have to just follow the scientific steps. Okay, so we are done with the calculation part. Now we have to just state the hypothesis, fix an alpha, obtain the degrees of freedom, and then do the conclusion. So clear this part. So hypothesis testing problems ಎಲ್ಲ hypothesis ಬರಿಬೇಕು. So the gender and result are in